So welcome. So this is the second chapter in our course so far, and we're going to talk about one-dimensional motion. One-dimensional because it kind of makes life simple for us. We'll later go on to two-dimensional stuff. This is one dimension part one, and there's the one dimension part two because there's an awful lot in this chapter. We're going to talk about things like displacement, velocity, and acceleration. They're the scientific terms. You might think of them as distance traveled, speed, and pickup, and they're not really the same thing. These have a slightly different meaning from these, and so we need to distinguish between them. Once we got the idea of the average of these guys, we'll talk about instantaneous information, like what's the velocity now? What's the velocity now? As opposed to averaged over a journey. That involves some calculus, some differentiation. And then we'll talk about actually an interesting issue where people do, it's not obvious, but speeding up and slowing down is a little bit more complicated than we tend to think. And then at the end of this section, we'll talk about motion graphs. And I'd like from the very beginning to tell you that graphs are not trivial little things we put in just to, break up the monotony. They are really valuable. So we actually develop some equations based on graphs in the next section. So let's start. We're going to talk about average displacement versus distance traveled, average velocity versus speed, and average acceleration versus what I'm calling pickup. Most people call it acceleration, but I don't want to say acceleration and acceleration. I want to say acceleration and pickup. If you are like I was as a student, you'd glance at that equation and go, oh yeah, triangle x is equal to the difference between some x positions and all that. And that's too casual. This delta x is one symbol. It's like welded together. It means one thing, which is displacement. And displacement is defined as, there should really be three little lines there, because it's defined as your final position minus your initial position. And the order matters. We're going to drill ourselves in physics to always do the end minus the beginning. Unless there's a really good reason not to. So displacement is defined as the final position minus the initial position. If you don't want to use the word position, you could use address, you could use coordinate, but however you express it, the meaning's the same. The distance traveled is a scale, and the displacement is a vector. Vector is something which has magnitude, it has a size, and it has a direction. So displacement has a size, your 6 meters for this displacement, and a direction, in that direction. Not that direction, not that direction, not that direction, but that direction. So we divide the world up into vectors and scalars. Vectors have magnitude and direction. Scalars only have magnitude. And it's really useful whenever you come across a new parameter to decide for yourself, is it a vector or is it a scalar? Because you treat them differently. Mass is a scalar. We don't talk about mass in that direction. We could say there's a mass over there, which is a different thing. We don't talk about 6 kilograms upwards. That makes no sense. I might talk about 6 newtons upwards, but that's a force. So mass, the kilograms, no direction. Temperature has no directions. I can say my temperature is going up in that direction. That's a temperature gradient. I don't say 28 degrees C in that direction. I might say a difference of 28 degrees C. I might say 28 degrees C more in that direction. But I don't just say 28 degrees C in a given direction. Displacement is a vector. Distance traveled. If I'm going backwards and forwards on a line, there's no direction to it. It's just where you go. It's just like, what does your odometer say at the end of your journey? That's a scalar. and so on. So try to divide the world up into vectors and scalars, and we are going to treat them mathematically differently. So how do we do these things? So let's do 3 examples. So an object starts at +3 meters, it moves 7 meters to the right, it then moves to a point located at -12. So I'm a visual thinker. How many people here play sports? So did you notice that, was there anything you were weak at that just didn't come naturally to you? That you struggled, a skill that you struggled to get? And then you practiced, and it got better. Yep. And my plea to you is, you might be lucky and maybe you're an all-rounder, or you might be really good at the math but not so good at the diagrams, or maybe really good at the diagrams but not so good at the math. I say math, I mean the algebra, the abstract stuff. And whatever you're not good at, practice, because you'll get most bang for your buck. You'll improve fastest on the thing you're not so good at. The thing that you're good at, you're already good at. So don't give it up, but just try and get good at both. I'm a visual thinker by my nature is visual thinker. So I tend to think in terms of words go to diagrams, diagrams go to equations, equations go to numbers. I get an answer. So on this, I'm thinking about a one-dimensional line. It's one-dimensional motion. So here's my number line, and here's my 0, and then it says an object starts at +3. So I'm going to go here, I'm going to go +3. And I start here, so let's put a big S in my little object. It moves 7 meters to the right. I don't have to be perfect, but that's about 7 meters to the right. Oh, 7 meters to the right. Oh man, get rid of that. I want to be over here. I'm now at +10. Went 7 meters to the right. So I started at 3, count another 7, I'm at 10. It then moves to a point located at -12. Oh my word. -12. So there's my visualization. This is the end. So what's its displacement? Well, displacement is equal to my final position minus my initial position. So my displacement is equal to, look at my diagram. I'm not looking at the blue words, they're gone. I'm looking at my diagram, I'm going -12 minus +3. There's my end, there's my start. What about this 10 in between? I don't care about that 10 in between. Delta x is equal to -12 minus +3 is -15 meters. Got to have the negative sign, got to have the units. Diagrammatically, the displacement is an arrow which goes from the beginning to the end directly. And you can see from that dotted arrow that is -15. You can see from your diagram it's -15. So for me, I look at my diagram, oh, it's -15. I look at my math, oh, it's -15. It's -15 meters, yeah. What distance traveled? Distance traveled equals the distance traveled. It's like, you know. So I have to go, let's have a look, 3, 7. So it's 7 plus. I go from the 10 back to 0. That's 10 plus. I go from the 0 to -12. That's 12. Distance travel equals, what is that going to be, 19? No, 29? 29 meters. I don't bother with the positive sign because scalars are always positive, unless it's a temperature, in which case it could be negative on a scale, but its value is positive. And this is a kind of way that I'm kind of, in a way, keeping track. I'll try to put a positive sign in front of a vector if it's positive, rather than just assuming it's positive, because there's no negative sign there. But scalars, I don't bother with a sign, unless there's a really good reason. Yes? Yes?
So basically on a test, I have to present it like that.
So, what would I look for on a test? Okay? If I was looking at this on a test, I would look to see, what answer did you get? And I'll take out all the ones that have the right numerical answer, and then I'll look through them and say, is the work there? Check, 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 check. That's pretty easy, yeah? And then I look at the ones where there's like nothing written down, or it's like it's just a mess. And is it worth anything? You know, no, 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 no. And then I look at the ones in between where you kind of start off right, but you don't get the right answer. I'm trying to figure out where did you go wrong and how significant is it. There's never well, no. If there is a really well laid out question, and I can see you did something like on the last step, you just forgot to square that number, but I can see it's all laid out, and you put the number down with a square on top of it, then that's not so bad. But if there's just an answer, I don't know what you did wrong. So from your point of view, it's not that I'm going to go along and say, no diagram, you lose half a point. I'm not going to do that. But if you give me less information, there's less justification for me giving you any kind of partial credit. Okay. And if you give me no work, then I let it go once or twice, but then I start saying, hey, I don't know that this person's not just looking at their neighbor. Okay. Now, I'm vain. I think this is a good layout. It helps me get the right answer. So now I'm your coach saying, I think this is a good way. You know, you need to hold the bat slightly differently. You know, this is the way that people make fewer mistakes. We're all adults. You can do it whichever way you like. But you know, with all those cadres, you know, if you remember anything from me, I'd like you to remember the approach, because I do think it is a good foundation. You know. So yes, I look for if there's a diagram. If there's no diagram, I feel a bit sad, because especially if the slip is because you called a positive thing a negative or a negative thing a positive because there was no diagram. You know. So, but I'm not giving you points. I'm not taking points away because you didn't do a diagram. You know. I don't do it like that. Okay. Notice. The 10 meters had nothing to do with it. It was just, you know, not a red herring. It's to confuse but not to confuse the intuition. It's to make it more interesting, really. I avoid questions where it's just like, you know, M is 6 and A is 5 and F is 6 times 5. There's no physics there. It's stuff like this. I'm giving you instructions in language. So now let's talk about that. If I was to do this course in French, I would fail because my language skills are not there. I worry for people who are not native English speakers. I worry sometimes. I used to work at USF, and I was doing a test, and this Japanese lady asked me what a teeter-totter was. Because I'd written on my test, you know, 2 students sit on a teeter-totter. Never thought about it. She's going, what's a teeter-totter? And I'm going, it's a seesaw. And she's going, what's a seesaw? And I'm going, oh, it's that kids thing. And I don't mind, I'll explain that. She didn't turn around to me and say, what's momentum? You know, that's in the book. You know, you're supposed to know that. So I worry a little bit about getting the language right so that, you know, it's kind of like, I'm not throwing in stuff like that. And if you feel I am, then by all means ask me, and I'll gladly explain it. But it's a good idea to think about me as a teacher. What's this problem? This problem is I give you some instructions so you can draw a diagram, and then you can apply a definition. Isn't that really what this problem's about? There's no integration here. There's no differentiation here. There's no find the area. It's like I give you some instructions in words, and then somehow you have to find the answer which I've defined displacement is. So how many ways can I give you instructions? And there's only a few ways. One is that I tell you how far you travel and in what direction. You start off here, you travel 7 meters to the right. I'm going, okay, go in that direction for 7 meters. I don't tell you where you arrive, you've got to figure that out. The other way I could say is, you start at 3 meters, you then go to plus 10 meters. It's the same setup, I just told you it in a different way. And the third way it strikes me is, I say, you start at plus 3 meters, over the next 2 seconds, you travel at 3.5 meters per second to the right. I give you a velocity and a time. So, 3.5 times 2 is 7. I went 7 meters to the right. Those are really the only 3 ways that I can typically think of to give you instructions. I tell you how far and what direction to go. I tell you where to go. I tell you what direction to go in at what speed for how long. That's about it. Can't really do much more than that. So if you can think about that and just be thoughtful, which way is he asking me to do this? I think it takes some of the mystery away from it. Questions on that? Cool. Next one, look, and this is so got to be careful. It's a different problem, but it kind of looks similar. This is average velocity. The little bar on top of it, V with a bar on top. It's like it's balanced. It's like it's averaged out. So again, it's a symbol. It means average velocity. And my average velocity is equal to my displacement over my time interval or duration, whatever you want to call it. And my displacement equals my final position minus my initial position, and my duration is my final time over my initial time. My initial time, my clock might not start at 0 seconds. No law says it has to. I'm going to compare this with the average speed, which is a scalar, which is just the distance traveled over the time you took. So let's visualize this. So I have my number line. Object starts at plus 9, so let's put 0 here. Let's put plus 9 meters there. Object moves 6 meters to the right in 4 seconds. So now I'm at plus 15. And now my clock is saying something that's different from what it started. I have some choices here. The most obvious thing to do is to say that was 0 and this is 4. Because it took 4 seconds to get there. But if you wanted to, you could put down this is 2 and that's 6. You could put down this is 7 and that's 11. As long as there's 4 seconds difference, that's all that counts. And I put an arrow in to show this is what happened. The object is stationary for 5 seconds, so it's not moving for 5 seconds. So that means it's now at 9. Was at 4. Add 5 seconds on, I get 9. The object moves 3 meters to the left in 2 seconds. So now I go here. I go from 15 to plus 12. And my clock has gone to 11. So let's just look at that again. So I started off at plus 9. I moved 6 meters to the right, so I went to 15. My clock was at 4. I sat around for 5 seconds, so my clock's at 9. I'm still at 15, but my clock's at 9. I then moved 3 meters to the left, so 15, 14, 13, 12. I'm at plus 12, and my clock is 11 seconds. Okay? So then I say, well, my V average is equal to my displacement over my time, which equals my final position minus my initial position over my final time minus my initial time, which equals, and now I'm looking at my diagram. I'm not looking at the blue words. And I say, what is my final position? My final position is plus 12. I put that in parentheses because it's a thing, it's an address. It's not 12, it's plus 12 is the address. Okay, it's a thing, it's like a brand, plus 12. and then I subtract. That's a subtraction. That's a mathematical operator. And then I do my x initial, and my x initial was +9 over, and then I have my final time. My final time said 11 minus my initial time, and my initial time said 0. So my average velocity equals 12 minus 9 is going to be it's going to be +3 over 11 minus 0 is 11. So that equals plus 0.27, probably 28, depending on how you round it, meters per second. That positive means that you actually went in a positive direction, which we did do, didn't we? There's my vector indicating my displacement, and we went in a positive direction. My speed equals my distance traveled over my time taken. Man, this is like 7 goes to 15. So 9 goes to 15, which is 6. And then 15 goes to 12, which is 3, over 11. So that's going to be 9 over 11. So my distance traveled would equal, that's not right, 0.8. My speed would equal 0.8, 88 carry 2, 1, call it 2 meters per second. Very different answers. Very different answers. It turns out if you go back to your starting point, your velocity was 0. So if you get stopped by the police and the policeman says, "Do you know how fast you were going?" You can say, "Well, I passed here last Tuesday, so my average velocity for the last week has been 0 meters per second." He'll give you a ticket, but you might laugh. So very different, yeah, very different. Average acceleration. Let's do our number line. An object has a velocity of +5 meters per second at t equals +7 seconds. Where is it? It doesn't matter. Just pick a point and go, okay, that's 7 seconds, and my velocity is +5 meters per second. And then over here somewhere, now the clock is saying 25, and it's -17. My acceleration, my average acceleration is equal to my change in velocity over my change in time, which equals v final minus v initial over t final minus t initial, which equals v final is -17 minus +5. And again, that -17 is the direction of the 17. It's a sense. And that other negative is a math operator. That's a subtraction. So I like to put things in parentheses when it's part of the sense, when it's part of the direction. Mathematically it makes no difference, but it just makes it so I can keep track of things better. My oh, I forgot to do the bottom bit. And let's have a look. My time is 25 minus 7. So my average acceleration is equal to -17 minus 5 is going to be what? -22 over 25 minus 7 is going to be 18, which equals minus 1.33. 18 goes into 6. 1.3. 11 over 9. Whatever that works out to be. What does that work out to be? Okay, you've got to be louder.
1.22.
2-2, thank you. I'm deaf, so. Yeah. And pick up is, well, pick up equals my change in speed over my change in time, which equals my speed final, my speed initial over my change in time. I look at my speeds and I go, well, hold on. That's going to be 17 minus 5 over 18, which equals something like 12 over 18, which equals 0.66 meters per second squared. It doesn't really mean much, actually. That doesn't mean much. Why do I write down the equations every time? Because I don't want to be forgetful. If I can put these into my long-term memory, they're solid for the test. So if every time you do the homework question, you write down the equation rather than just write down the numbers, by the time the test comes around, you know the equations. You already used them so many times. So it's really worthwhile to just slow down a bit. And if you come to my office, you will see that I am untidy. By my very nature, I am untidy. My old boss would say, just not on the floor. Just, put it in a cupboard, but not on the floor. I'm walking over stuff here. And I'd go, that's a filing system. That's like how I lay things out. And it wasn't really. I just, was untidy. But on some things, I'm really picky because I don't want to lose points. So be a bit mindful of that. Can you have a go at this one for me, please? Can you have a go at that? So the way you do it is you click on the little button that turns it on, and then you pick your answer choice on there. I'm going to turn the clock off. I'll pause it. So resuming, so basically here's the answer for this. I forgot to talk about it when we moved on. But basically the same pattern. You do your number line, and then you write your definition, then you put your numbers in. Let's look at this one. So we say, let's get our diagram going. So we have this. At t equals 5 seconds, the car is at minus 16. So here's minus 16. And my clock says 5. I'm not starting off at 0 seconds now. At t equals 9 seconds, it's located 6 meters to the right of the starting point. So that means that it's going to be minus 10. And this is going to be 9 seconds. And I went from there to there. And then after another 2 seconds, it's at minus 12. So here we have minus 12, and now I'm at 11. So I went like that. I don't care about the fact that I'm all bunched up to one side of the 0. I don't care. I just don't care. Minus 16 goes to minus 10, goes to minus 12. And my clock goes from 5 to 9 to 11. Now, what do I want to know? My average velocity. So my average velocity equals my displacement divided by my duration, which equals my final position minus my initial position over my final time minus my initial time. And then I'm looking purely at my diagram. And I say, well, my final position is going to be minus 12. Subtract from that my initial position. My initial position is minus 16 over my final time is 11 minus my initial time is 5. Minus 12 minus minus 16 is minus 12 plus 16, which is plus 4 over 5. 11 minus 5 is 6, so that's going to be plus 0.66 meters per second. Cool. It's mathematically not hard at all, but it's very uncomfortable because you're getting this. It's a new terminology, new language, new skills, new pattern. I'm going to skip this. It's all right. It's just same old. Let's have a look. Yes, I'm going to actually pause here. Let me have a quick look. Let me see what time it is. It is 29 minutes. Oh, maybe not. Let's do just a little bit longer. So let's talk about some instantaneous stuff now. So imagine I plot a graph of position versus time. So here's position and here's time. And my graph is just some kind of curve. Let's just think about this for a second. Where am I traveling fastest? Am I traveling fastest during this period, let's say A, or am I traveling fastest during this period, let's say B? So click in. Can you do that for me? Can you click in? If you think you're traveling fastest during period A, will you click A? And if you think you're traveling fastest during period B, will you click in B? So where are people traveling fastest? One more, come on. Yeah, there we go. Stop. Oh, I'm kind of curious what this says. Yeah, okay. And it's more divided this time. So the answer is A. And the reason the answer is A is for a given time interval, you have a bigger change in your position. That's what going fast means. You have a big change in position for a given time interval. And if I look at these two, there's next to no change in my position for B compared with A. So graphs are not easy to interpret sometimes. We don't practice them anywhere near as much as we really ought to. I'm not sure why that is. It's just traditional. It was the same for me. I think it's the same for you guys. You don't get as much practice with graphs. Or maybe you get it early, and by the time we get here, it's kind of distant history. But graphs are incredibly useful, and one of the big complaints is people, they're just uncomfortable interpreting graphs. So this journey started off, and it went very quickly in a positive direction, and then the object kind of slowed down. It actually went like that. Like an elevator slowing down as it goes upwards. That's what's actually going on. And I want to know what the speed is or the velocity is at that instant there, that instant of time. So I draw myself a tangent. And with tangents, when I want to know, well, interesting point here. The way you get your speed, your velocity, is you take the change in position divided by the change in time. And that's a slope, agreed? Rise over run. So I construct a triangle, and I measure my rise, and I measure my run. That gives me the velocity. Alternatively, if I have the equation for this, I can differentiate it. So we say the v in the x direction is equal to the limit as a little bit of time goes to 0 of delta x by delta t, which equals dx by dt. If I do instantaneous acceleration, now I have a velocity versus time graph. It's not the same graph. It looks similar, it's the same shape, but it's not the same graph. In this case, where am I going fastest? Am I going fastest in A, or am I going fastest in B? Can you clock that in for me, please? Look at the graph. Am I going fastest in A, or am I going fastest during period B? Where am I going fastest? Couple more people? Yeah. One more. Okay. And if I do that, ooh, that's interesting. And if you think about it, the answer's got to be B in this case, because fastest means the same as, well, not the same as velocity, but if you've got a bigger velocity, you've got a bigger going fastest. And this is a bigger number than that is, you know. So in this case, it was about the slope. And in this case, it's just about reading the graph, because the graphs are different. Most of the time, the biggest mistake we make with graphs is we glance at the axes and we misinterpret them. That's what happens very often with graphs. So this is a different graph. It's a velocity versus time graph. And again, if I want to know the acceleration, I can pick up time and I can say what's the rise and the run of the tangent to this, or I can do the integration. I can do the differentiation. So here's an example of the integration. So what is the instantaneous velocity of the particle whose position is defined by? Now, you don't have to draw the graph, but, you know, and I'm not going to draw the graph properly. I'm just going to kind of imagine it. So here's my x and here's my t, and it's t to, if it was a simpler one, I just do it. Well, no, I'm not going to do it, but I'm imagining that something like that. And basically, I want to know what is my instantaneous velocity. So I'm picking a point, and I'm saying, what is my, you know, rise over my run kind of thing. Well, I know that y is equal to 2t squared plus 4t minus 7. So I know that v equals, well, dx, oh sorry, x it is, dx by dt. So I just use, what is it, the power rule? I can't even remember what it's called. Multiply the power by the coefficient and reduce the power by 1. What's that? Power rule. So I go 4t plus 4. Don't tell Professor Sowash, I don't remember what it's called, because he'll make fun of me in the hallway. And then I go, well, at t equals 3 seconds, we get v is equal to 4 times 3 plus 4, which equals 12 plus 4, which equals 16 meters per second. Did I get that right? I think I got that right. I like doing those steps. The more you do in your head, the more slips you'll make. The more you write stuff down, the better. If I wanted acceleration, what would I do? I'd go a is equal to dv by dt, which equals, oh, I'm doing that. So it's going to be d by dt of 4t plus 4, which equals 4 plus 4 meters per second squared. Constant acceleration on that guy. Yep. Let's skip it because we're running out of time. I'm going to stop there.